bell-shaped distributions, and very often that's referred to as the normal distribution. Okay, so this is a bell-shaped distribution. Our mean is in the middle. Okay, and what we find is that 68% of the data values will fall, and I'm just going to call it X bar, within one standard deviation of the mean. Okay, so X bar plus S and X bar minus S. If we go out 2 standard deviations, so this is going to be X bar minus 2S and X bar plus 2S, then we find that 95% of the data values fall within that range. And if we go out 1 more standard deviation, X bar minus 3S, X bar plus 3S, okay, then we find 99.7% of the data fall within 3 standard deviations of the mean. So what that means is that we have just about 0.13% in each tail here. So a very small portion is outside the 3 standard deviation mark when we're looking at a bell-shaped distribution. So that's called the empirical rule, the percentages here. 68% of the data fall within 1 standard deviation of the mean. 95% of the data values fall within 2 standard deviations of the mean. And 99.7% fall within 3 standard deviations of the mean. Okay, now we have 2 more items we need to look at. First of all, Chebyshev's theorem. Note that unlike, I'm going to correct my spelling there, unlike the empirical rule, which applies only to the normal or the bell-shaped distribution, Chebyshev's theorem applies to any distribution, including the normal distribution. And what it says is the proportion of any set of data lying within k standard deviations of the mean is always at least, and notice the use of the words at least, 1 minus 1k squared, 1 over k squared, where k is any positive number greater than 1. Now that k represents the number of standard deviations. So if we're talking about within 2 standard deviations, that means k is 2. We get 1 minus 1 over 2 squared. 2 squared is 4. 1 minus a fourth is 3/4. So at least 3/4, or 75% of all data, fall within 2 standard deviations of the mean. For k equal to 3, we'd plug in 3 in our formula up here, and we get 1 over 3 squared, which is 1/9. So for k equal to 3, 1 minus 1/9, or 8/9, that means at least 8/9, or 89% of all data, fall within 3 standard deviations of the mean. So that's our Chebyshev's theorem. And again, that applies to any type of distribution. Any type of distribution. Okay, finally we have the coefficient of variation. And this particular idea helps us to compare data that is in different units, or like if we want to compare an SAT score to some other testing score, we can do it using the coefficient of variation. Because what happens is whatever our units, if we're talking about inches, divided by inches when we talk about our S and our X. The units cancel out, and we're just going to end up with a percent. So that's the reason that, so if I were doing, for example, the coefficient of variation for our initial example, 14.6 divided by, let's do the 86. How do we represent that as a percentage? 14.6 divided by, this should be X bar, not 80, not an X. That is an X bar. Realized I was, so our 72, and that would equal, okay, it should be a mean that we're working with. We could also do it with sigma over mu. So if we take 14.6 and divide it by 72, 6 divided by 72, I get 20.3%. So if we had temperatures in a different scale and we wanted to look at the coefficient of variation for that particular group to compare them, since the units are different, we could convert that scale using also this formula, the coefficient of variation, to find the coefficient of variation. And then once we end up with a percent, we could compare the two scales. So that's what that is useful for.